Hello everyone, I'm Greg Karlovitz from the Hydrologic Engineering Center. Welcome to our course on statistical methods in hydrology. This video is part 1 of 3 on the topic of multivariate analysis and will discuss marginal, conditional, and joint probability. Let's get started. In this segment, we will discuss how multiple events and random variables interact with each other. We've seen some of these before, and we will expand on these concepts to build to bigger and more complex multivariate problems. Let's start by looking at 3 key distinctions of notation. In the context of multivariate probability, when we encounter P of A, this is referred to as the marginal probability of A. When we see any of the following, P A comma B, P A and B, or P A intersection B, these are different notation for the same thing, the joint probability of A and B. Finally, when we see P A vertical pipe B, which is read as A given B, this is conditional probability. In multivariate probability, when we ask about the probability of one event, regardless of any information we have about other variables, this is referred to as marginal probability. P of A is the marginal probability of event A occurring regardless of any other information. Imagine the rectangle has an area equal to 1. If the area of a circle, less than or equal to 1, greater than or equal to 0, is equal to its probability, then in this case, P of A is the area inside A regardless of whether it's in B or some undrawn C, and so on. Now imagine that we're concerned with the region that belongs in both A and B, so that both things have to happen. This is the joint probability of A and B, or the probability of the intersection of A and B. The area of this lens is less than A or B. It can be at most the area of the smaller of the two, assuming it's completely within the other. Joint probability can be very important in situations like expert elicitations, where expert judgment is used to estimate the probability of something occurring. However, there's one key fallacy that can ruin the validity of these estimates, called the conjunction fallacy. Tversky and Kahneman in 1983 performed an experiment with a number of statisticians. They gave the following question to the field. Linda is 31 years old, single, outspoken, and very bright. She majored in philosophy. As a student, she was deeply concerned with issues of discrimination and social justice, and also participated in anti-nuclear demonstrations. Which is more probable? A. Linda is a bank teller. B. Linda is a bank teller and is active in the feminist movement. The answer is statement A. Linda is a bank teller. This is because the extra condition imposed by the statement that Linda is active in the feminist movement necessarily makes the second statement less likely. It is easy to look at the narrative and find the likelihood of the statement Linda is active in the feminist movement to be high. However, this conclusion suffers from the conjunction fallacy. The only way that the statements could have equal probability is if the probability of Linda being active in the feminist movement is 1. If it's anything less than 1, then the statement that is second has to be less probable. The largest that the joint probability of two events can be is the smaller of the probability of the two events, and this only occurs if B is completely contained within A. Then P of B equals P of A and B. The Venn diagram above shows this situation, where the overlapping area, which is the probability of A and B, is equal to the probability of B. Independence of two events comes from understanding joint probability. A and B are independent if and only if the probability of A and B is equal to the probability of A times the probability of B. This is written as A perpendicular to B, which means that the two events are independent. This is not easy to show on a Venn diagram and has to be constructed so that the overlapping area of two circles is equal to the product of the areas of those circles. Conditional probability is all about adding information. It asks, once we see some event B occurring, what is the probability that event A then occurs? When B occurs, our universe narrows a bit, and we can only then observe outcomes that are dependent on B having occurred first. It transforms our Venn diagram from the figure on the left into the one on the right. After B has occurred, the possible outcomes are that A occurs or A does not occur, which is written as A complement. The probability that A occurs given that B has occurred is the area of overlap between A and B divided by the whole area of B. It is important to note that conditional probability is not reversible. The probability of A given B is not equal to the probability of B given A unless the probability of A and B are equal. This is due to Bayes' theorem, which lets us do two important things. One is to reverse conditional probability, and two is to update our beliefs with information. The first of these usages is important for working with conditional probability. The second is an entire branch of statistics which unfortunately will not be covered here. Hat tip to Reverend Thomas Bayes. All three of the flavors of multivariate probability that we've talked about, marginal, joint, and conditional, are related. To get the marginal probability for event A from the joint probability of A and B, B is integrated out of the joint probability. This is used most frequently in finding the marginal probability distribution for variable A when what is given is the joint probability distribution of A and B. An important identity is that the probability of A given B is equal to the joint probability of A and B divided by the probability of B. To reverse the condition and get the probability of B given A, you would find the quotient P A and B divided by P of A instead. When A and B are independent, the joint probability of A and B is equal to the products of the probabilities. This means that the previous identity shows that the probability of A given B is equal to the probability of A. In other words, conditioning doesn't add any information. If B occurs, it makes it no more or less likely that A is going to occur. Knowing which situation your events are in can be important for interpreting the results. We talked before about the conjunction fallacy, and it's important to remember that joint probabilities can never be larger than marginal. This is important because if you have a situation where the outcome of interest requires a bunch of things happening, and one of those has a very tiny probability, the probability of your outcome of interest is smaller than even that very tiny value. When a condition is imposed, the event probabilities can change vastly. If the probability we are given for A to occur is dependent on already having seen B, this actually doesn't give us any information about the marginal probability of A occurring. In the Venn diagram at the bottom, we see a situation where P of A given B equals 1. If B happens, there is no way for A complement to happen, that is, for A to not happen. But what does that say about the probability of A occurring at any time? It could be large, but definitely not 1, as in this case. In this case, B occurring only tells us A is certain to happen. But if B doesn't happen, A seems to still be pretty likely to happen. That's because the ratio P of A divided by P of B is pretty large. This also means that P of B given A is much smaller than P of A given B. If we see that A has happened, there's still a pretty good chance that B doesn't happen. The law of total probability lets us break up problems into discrete elements that may be easier to model. In this simple situation, we observe phenomenon B in the context of either event A happening or not happening. We can compute the probability of B by attributing its probability to those two situations. The first term after the equal sign gives us the real area of the overlap of A and B, and the second term gives us the real area of the part of B that is not in A. Because A and A complement are mutually exclusive and exhaustive, B has to either be an A or A complement. This means the remainder of the area is an A complement and can be computed as the real area of overlap between B and A complement. In this case, we only see two variables, but the law of total probability extends to arbitrarily many variables, which can be used to break up a problem into parts that are easier to model. This is the extension of the law of total probability into arbitrarily many variables. We are interested in the probability of event A, and it's observed after one of the conditions B1 through B4 are observed first. If we establish the B's are a partition of the sample space, in other words, they don't overlap and there's nothing that can happen that's not in one of the B's, then we can generalize the equation. This lets us compute the probability of A from an arbitrary number of conditional probabilities. Coincident frequency analysis gets a lot of mileage out of the law of total probability. This will provide a brief overview of the method, which we will see in more detail later. In this situation, there is a levee pump station storage basin, and we are interested in the probability of the stage of that storage basin exceeding some values. This is our unknown event C. It's a function of A, which is the interior flow to the pump station, and B, which is the exterior flow on the river side of the levee. There's a joint distribution of A and B, and we simulate the response of C for a large number of combinations of A and B. A is treated continuously, and B is broken into a number of discrete cases. Response functions are plotted for each discrete case of B, which are plots of C as a function of A with a given value of B. The probability of a value of C is computed then as the sum of P of C given B times P of B for all B. This process has mainly been replaced by more intuitive techniques involving Monte Carlo simulation that take advantage of modern computing power. This is a little bit of a preview of the discussion of joint probability distributions that we're going to see later. However, it ties in very directly to the discussion of the difference between marginal, joint, and conditional probability. Imagine the joint behavior of variables x and y, and they're defined by the blue contours in the plot. The contours are lines of constant likelihood. The mode of this distribution is in the oval in the middle of the contours. This is referred to as the joint distribution of x and y. The marginal probability distribution for x is the solid curve along the x-axis, and the marginal probability distribution for y is along the y-axis. Remember that the marginal refers to the behavior of this variable without regard for any other variables or information. Now imagine we observe that x takes on some value, shown as the vertical dashed line. The conditional distribution of y, given that we have observed x take on this value, is shown as the dashed line along the y-axis. Notice that the shape of this distribution is different than the marginal distribution shown along the same axis. The center of this distribution has shifted upwards, and the spread of the distribution seems smaller than the marginal distribution. This conditional distribution of y has different moments than the original marginal distribution for y. That is to say, it has conditional moments conditioned on having observed that random variable x has taken on some value. That vertical line representing the observed value of x makes a slice through the joint probability distribution, and the cross-section that it makes is the conditional distribution of y. The mean of this conditional distribution is the conditional mean of y given a value of x, and the variance of this distribution is the conditional variance of y given a value of x. With this conditional distribution shown as the dash curve, we can answer a question like this. What is the probability that y is greater than 3 given that x is equal to 0.7? We would find the dash curve by taking a vertical slice of the joint distribution at x equals 0.7, and then on the dash curve, find the area of it for the region where it is greater than 3. When we have joint distributions of two variables, we might want to know more about the behavior of one of those variables given that we have information about the other. Linear regression is one of those cases. When we have a linear regression model, we're describing the relationship between two variables. Usually, we want more information about the response variable y after we've observed that x is some value. This is how we make predictions about the best estimate for y based on the regression line or build confidence and prediction intervals. They are all based on conditional moments. The regression line itself is the conditional mean of y at all values of x. X and y are random variables, but the mean value of y given any value of x is the regression line. The variance of y tells us what kind of regression model that we're going to build. We'll see in the regression discussion that we assume that the conditional variance of y given all values of x is constant, and y has a normal distribution. This is fundamental to simple linear regression. However, in the cases where either or both of these assumptions don't hold, we might build a different kind of regression model. Here is the simple linear regression example of conditional moments. We see that the conditional mean of y is the regression line, with beta naught plus beta 1 times x determining how the conditional mean varies linearly with x. The plot shows the best fit line going through the middle of the bell curves that show the conditional distribution for y. The bell curves all have the same spread because in simple linear regression, we assume that the conditional variance of y, given any value of x, is a constant. Generalized linear models help us in the situation where we can't meet the assumptions in simple linear regression. In generalized linear models, which are a type of regression with more relaxed requirements, the response variable does not need to be normally distributed. It could have any distribution that you choose. The parameters, or the moments of that distribution, become a function of one or more predictor variables, meaning the mean and the variance, and possibly higher moments, are explicitly functions of one or more predictors. These are very flexible models useful for a variety of situations. Generalized linear models are a more advanced topic, and we won't cover them in this class, but they are good to know about for when your regression analysis calls for them. Finally, we see the law of total expectation, which is also called the law of iterated expectation, and it allows us to get the mean of y when all we have is the conditional distribution of y given x. This basically says that the mean of all the conditional means of y is the mean of y. Conditional moments have similar properties to conditional probabilities, including a law of total expectation that behaves much like the law of total probability. The second equation is the general case of the first equation. Say you have two cases, B1 and B2, and they are equally likely, that is, they both have probability 0.5. When B1 occurs, the mean of A is 3. When B2 occurs, the mean of A is 5. Based on the second equation, this means that the mean of A is 4, computed using a weighted average with the weights equal to 0.5. There are similar rules for variance and covariance that let you compute the variance of a random variable from its conditional distribution. In this video, we discussed marginal, conditional, and joint probability. We talked about a lot, so thanks for sticking with me. Two key points to take away from this video are: marginal, conditional, and joint probability are means for expressing the relationship between two events and their probabilities of occurrence, and conditional moments are a way to express the behavior of one random variable given that we have information about another related random variable. Thanks, and tune in to the next video in this series on multivariate analysis to learn about correlation.